One way of looking at how networks work is to divide the various functions up into layers. So let's look at the implications of this. Let's get some terminology here and some concepts. Layers and stacks. Every device that can communicate on a network has code, programming code, that was written to handle the communications process. And since more and more devices these days are set up to or have the functionality to communicate on the network, we're talking about a lot of devices here. And to help us think about the problems of network communications, we usually talk about different layers that do different jobs. We'll see this on the next slide. These layers help us break up the programming that's required into smaller pieces, kind of modularizes things. And there's advantages to modularizing things. It allows you to update or improve the code at any particular layer without having to rewrite the whole all of the code. Now, a lot of times when we're talking about TCP/IP, and this is the Transport Control Protocol / the Internet Protocol. These are the two protocols that are responsible for most of the traffic on the Internet. So you certainly should endeavor as much as possible to understand what's going on with TCP/IP. In the case of TCP/IP, we often refer to these layers as a stack. That's one way of looking at it. It's also one way of referring to it. You will see this frequently in the literature, the networking literature. We'll talk about the TCP/IP stack, or sometimes it's just we abbreviate it the TCP stack. Now, the whole concept of layering is built on the typically, well, one of the things you can base it on is the OSI model, also referred to as the 7-layer model. When I'm explaining this to people or students, I typically lump the application, presentation, and session layer into what I refer to as upper level layers, or something along those lines. As a networking person, I don't really worry too much about these upper layers. What I'm interested in starts down with the transport layer. This is the realm of TCP and the user datagram protocol, which is simpler but nonetheless still very important. The network layer is the realm of IP, the Internet Protocol. Often we also see ICMP at this layer. I think memory serves me well. Doesn't really matter. Data link layer is where we get into MAC addressing, hardware addressing. And then finally, the physical layer is the network medium itself. So, this is one of the starting points for the whole concept of layering. And in class, you probably, after you were exposed to all this, your instructor probably pointed out to you that we really haven't built anything that looks like this. This is just a way, a kind of handy way of looking at the problem. Now, I mentioned some protocols already: TCP, IP, ICMP, etc. These are all protocols. A protocol is an agreed upon specification or format for transmitting data between two devices. Protocols are are necessary for the proper functioning of the Internet, or pretty much anything else. It determines what each of the individual bits in the headers that we're going to talk about here in a few moments really mean. So the protocols are very important. And we've talked about, I briefly mentioned TCP, UDP. We're going to look at these in more detail in other videos here. We got IP. The ICMP is the Internet Control Message Protocol. There's another protocol that's very important called ARP. These are all examples of protocols. And if you're really interested in more technical background on this, you could do a Google search on, like, for example, TCP, or the Transmission Control Protocol. You will undoubtedly find a document called RFC, Request for Comments, and I can't remember the number of the one for TCP right off the top of my head, but you can actually go see the original specification for TCP or IP, etc. They're kind of interesting to kind of skim over to see how things are supposed to work. Now, I mentioned a while ago that when we were talking about the OSI model, we've never really built or programmed a stack that conformed to the OSI model. The TCP/IP protocols were actually put together and put into practice while the working group was talking about the OSI model. The TCP/IP people just got tired of waiting. You can somewhat map the TCP/IP header, the TCP/IP stack here onto the OSI model. The application layer, this is where you're going to have in the OSI model the application, the presentation, and the session layers. Transport is obviously transport in the OSI model. Now, from here it gets a little dicey because we've got 2 layers in TCP/IP and we've got 3 left. And typically what happens here is they split the data link layer. And then you got data link here. And data link actually is already a split layer if you think about it. If you remember back to your study of the OSI model. So typically what they do here is there's a kind of dividing line here. And the TCP/IP internet layer is comprised of the network layer and the OSI model. So all this is OSI model. So the internet layer of TCP/IP is all the network and part of the data link layer, and the network layer of TCP/IP is part of the data link layer and the physical layer of the OSI model. Just in case you ever were curious about how the real implementation of TCP/IP maps onto the kind of theoretical framework of the OSI model. I threw this slide in, a few more things about TCP because it's so important. We're going to be looking at it in much more detail later. So this is kind of a first contact maybe with some really important things about TCP. Remember, TCP is the Transport Control Protocol, and it is the most used transport protocol on the Internet. So TCP establishes a connection using something we call a three-way handshake before it sends any data. The whole concept of the three-way handshake is very important. There's some pretty serious security implications of this we'll be looking at later. TCP also has a mechanism to ensure that every single packet is received by the destination. And this is a good thing. If you're transmitting data, you certainly want to make sure that every packet arrives, and not only that, every packet arrives without being altered by noise or something else along the way. TCP also uses port numbers, and these numbers range from 0 to 65,535 in decimal. The number is actually stored as binary, but if you convert it to decimal, this is the range. So TCP uses port numbers for both source and destination. And this is how the computers keep up with what to do with the packets. These aren't real ports. You can't plug a wire into one of them. So they're just numbers, and they're used by the TCP stack on each end to keep up with where a particular packet is coming from, what application on the source end, and what application it's going to on the destination end. And I'll draw you a little picture of this sometime. But this is a very important concept, the concept of port numbers. And remember, they're not real ports. They're not like ports on a switch or a hub. You can't plug wires into them. They're kind of, in a sense, virtual. But these numbers are used by the TCP stacks on each device to keep up with what application on the device the packet came from and where it needs to go, what application it needs to go to on the destination end. And I'll have much more to say about this later. So here is a graphic that will show you, hopefully, some idea of how these layers actually work. Now, here's the thing. We assume that at the upper layers here, we've got a long stream of data that we need to move from one computer to another. Now, we don't send it all at once. There's a couple of reasons for this. If we send a big long stream of data all at once, number one, we're going to be tying up the network while this big long packet is being sent. And the second problem is if there's a mistake, not a mistake, but if there's an error due to noise, etc., anywhere in this big long string of data, we would have to resend the whole thing. So what really happens in the real world is we break up the long stream of data into segments. So here you have data segments, and these two layers here, this is actually the transport layer. So the transport layer breaks a data stream up into smaller pieces and puts a header on it. So in this case, we're doing a TCP header, for example. This could be a UDP header. My examples use TCP because that's the most common thing. We'll be talking about in probably the next video what is really in the header, what type of information is in the header. But let's think about this for a moment. You could kind of make the analogy here that each one of these data packets is in essence a letter that we're going to send someone. You can't just take a letter and put it in the mailbox and expect it to get to the proper destination. You've got to add some other information to the letter. These are the things that you put on the envelope. You put a return address, you put a destination address, you put office numbers, you put house numbers, etc. you can look at this the same way. We're going to take our letter, which is our data, we're going to encapsulate it in an envelope, and that's where all these headers are going to come in. All this header information is things that we're going to put on the envelope, as it were, so that we can make sure that the network devices, routers, etc., can move the packet from one point to another, and that the devices that receive the packet, be it a computer or some other device, can figure out what to do with the packet once they get it. So all this header information has to be added to enable the packet to get where it needs to go, both from computer to computer or device to device, and also from a particular point inside of an operating system on a device to another point in the operating system of another device. So that's why headers are important, and we're going to spend some time talking about what's in these headers. So transport layer, we're going to add a transport layer header. In this case, I'm making the example of a TCP header. Now, I make a little note here. This is not to scale. Typically, your data is, a much bigger piece. It's not the same size as your TCP header. But for the purposes of the picture, I had to kind of do it that way. Now, what's going to happen here is, from the transport layer, all this is going to go down to the next layer in the stack, and this is the network layer. This is transport layer. Now watch what happens in the network layer. We're going to add another header onto this. In this case, it's pretty much always going to be the IP header. Notice that we still have the TCP header and we still have the data. So what we've done here is we've added another header onto the front of this. Same thing happens the next layer down. All this comes down, and this layer here is the data link layer. And I need to add something here. There's another little section here called the FCS, frame check sequence, that I didn't put in my picture here. But same concept. From the transport layer, each packet is sent down to the network layer in the stack. The network layer adds an IP header. This moves on down to the data link layer, which adds a frame header and a frame check sequence to the end. So again, think back, we're putting basically a letter in an envelope, and we're adding information to the envelope to ensure that the important thing, the letter or the data, can actually be delivered. So that's the thing you need to remember about headers. We've got to have this header information, and there's a format we're going to look at that has to be followed. Well, and it's in the protocol specification what each one of these, every bit and these headers, what every bit has, actually means, so it can be deciphered on the other end. So this is the whole how the layers work. We start out with a long string of data, break it into pieces, and then start putting header information on each one of these pieces. This part right here is technically called a frame. Often we don't use the word frame. Often we just say packet, although technically it is a frame, since we put the frame header on it. Typically when I talk about a packet, I'm actually talking about this. Now this is all that happens in software. At this point it's ready to, the thing that's down below this is the physical layer, where it actually, the network interface card puts it out on the network medium. So if you kind of get a grip on what's going on here, you're going to be way ahead of the game when we start looking at things in more detail. Now here's the English verbiage on this. We have some data at the application layer that needs to be sent across the network. Data is going to be passed to the transport layer through the application, through the presentation and session layer. That's in the 7-layer model. If you look at this from the standpoint of the TCP/IP model, this is all one layer. At the transport layer, we break the data into segments. We add a header to each of the segments indicating the source and destination process. We'll talk more about these later, process or service for the data. The data is also numbered so it can be reassembled at the receiving end. This is important. Data is then passed down to the networking layer. At the networking layer, we add the source and destination IP addresses. This has to do with moving packets from place to place on the internet, device to device. Then we pass the data down to the data link layer. The data link layer puts on the hardware addresses, the source and destination MAC addresses, media access control, or hardware addresses. At this point, it also adds the frame check sequence. I keep forgetting to mention that. The data is then passed to the physical layer. At the physical layer, the data is actually placed on the network media itself, and in other words, it's sent. So here you've got a picture of how the layers work, and you've got a written explanation of how the layers work. You've got to understand this. It's fundamental to a lot of topics that we're going to talk about in networking and security.